Right, I'll just grab another water. Hi everyone, thanks for coming. My name's Stuart Maclean, I work at the SeaJUG. I've dabbled with Java for a long time. I've dabbled with cybersecurity in various projects at the SeaJUG for probably 5 years, and what I want to talk about today is kind of some results of things that I've done in Java that will hopefully be applicable to you and your problems as well. And when we're talking about a Java technology, a parser generator, a program reading tool and translation tool called Antlr. It's not my work. Antlr is out there, there's an Antlr website and stuff. I'm just going to show what Antlr is, how I used it, and how it may apply to you. If there's any questions, if this gets too complicated, just butt right in straight away, yes?
Yes, applied physics program. What is that? What do you guys do?
Well, we do a lot of marine stuff. At my day job,
Okay.
so we do a lot of oceanography, a lot of stuff with the Navy. It's not really physics like Einstein physics.
Okay.
It's a ton of software people, actually. So that's where I work, but I'm not a physicist. Actually, so it's a good point that you asked that question, and I'll show you why in a minute. Okay, so do I have any C programmers in the house? Good, good. Okay. So for the rest of you that aren't C programmers, if I do get to the end of this talk and don't run out of time, you'll probably run away screaming, saying, "My God, I'm never going to be a C programmer." But it's good to know that there are some people in the room that are. Okay, so I've got a lot to talk about. Remember, it said I got to 8:45. I could always have a break at 8 o'clock or whatever if people want to. Otherwise, I'm just going to plow on. I'm going to try and make this as light-hearted as possible, given I'm talking about Java and even talking about C and C language generation. So my outline is, why am I standing here? What Antlr is. Antlr is an acronym for another tool for language recognition. So you write a program that recognizes other programs, basically. How you would start using Antlr, how it integrates nice to Maven. I'm a big fan of Maven. Used Ant for years and now can't believe it. Never used Ant for years. So how easy it is to get your system in Antlr going with Maven. You can't even really think about compiling stuff. You just say, I've edited my grammar, and Maven handles everything else. And then I'll go on and start with a toy expression language. Something that you might think of is writing a calculator, basically. It can do A plus B times C times D plus 4. Okay? So given that input stream, given that program, how do you write code to recognize and maybe evaluate that program? So it's a simple programming language. You probably wouldn't think of it. It can't do while, it can't loop, it can't even conditional, it can't branch. It's basically a sequence of tokens that can do binary operations. But it is a start, and writing a program to recognize valid sequences is a non-trivial exercise, unless you're using something like Antlr, which does all the heavy lifting for you. So I'll introduce this toy expression language that I basically got out of Par's book. Terence Par's the guy behind Antlr. If anyone's interested at the end, come and get a reference for this book from me. It's an excellent book, and it's a sort of book that gets better the more you read it. You kind of skim over a page the first time, and then the 10th time of reading you found, I've read the whole chapter, I understand it, it's fantastic. And this guy writes with humour, which is pretty unusual in computer science books. So I'll show that the toy expression language, how I'm going to write out what that language is, and then I'll show you how to do things with it, like being a calculator. And then I'll show you how to extend what we want to do with it by having Antlr generate what's called an abstract syntax tree, a tree, which is what you normally think of as a kind of intermediary stage of things as heavyweight as compilers. Okay. So we'll represent a program as a tree. I'll show how a combination of Antlr and some regular Linux tools can give me visualizations of those trees. Okay. And then I'll talk a bit about Antlr's API. Not only is Antlr a program that you give it a grammar and it generates source code, there's actually an API, especially for walking trees. Okay. And my particular goal for using Antlr was, given some Windows C code, I want to write some more Windows C code that looks very much like the original, but is slightly different. That sounds absolutely crazy, and it probably is, and I'll show you why I wanted to do that for the purposes of system called API hooking, which is one method of analysing a program that you know nothing about, and you want to say, what does that program do? Okay, so binary runtime dynamic analysis is a project that I worked on when we were doing a cyber project, and I wanted to auto-generate all of the Windows API into some new C code, and I thought, you just can't write this by hand. And I went to Antlr, and Antlr being a Java tool, this is why I'm kind of standing here today talking about its use. So I'll manipulate C code, source C code, using the tree stuff that precedes it. Okay? And then I'll conclude, hopefully, with some summary of everything that I've spoken about. Any questions? Okay. So the goal for my work was I want to auto-generate C code for binary program analysis, basically malware analysis. What does this program do? It doesn't come with annotated source code, as you can well imagine. So if you stare at the assembler all day, that's just a thankless task. Or do you run it? And if you're going to run it, it's nice to be able to see exactly what it does and the paths it takes and the Windows API calls that it makes as it's running. The kind of alternative to that, to run a program, is just snapshot my disk before I run the program, snapshot my disk after I run the program. That's what changed on my disk. Run a packet sniffer on the network. That's what the program did on the network. Combine those two and say this program does X and Y. That's a very kind of high-level view. You know, what happens if that program is listening on a socket? That's not going to show up on your file system. That's not going to show up on your network. But you want to know that program's listening on a socket, and in 2 weeks' time, someone might connect to it. So you get a lot more inspection power of a binary program if you use a system like API hooking, and I want to generate C code to do that. Okay. But my goal for this talk is to say, Antlr's fabulous. If you've got language text processing problem, Antlr is a system that you can use. Okay, so that's the goal really for the talk, not my goal for the work. Okay, so history of this talk is, last fall I was giving a talk on, I've written a Java program to do whole disk imaging and efficient differencing, and you could image your laptop drive once a day, store it in a database very efficiently, run some tools to run over it, and you could say, have I got any nasty stuff on my disk? Okay, and I said to Nimrit last summer, can I basically give a practice of my talk in the fall at SeaJUG? And of course Nimrit said, well, SeaJUG is so vibrant, I haven't got an opening until June next year. Okay. So last fall came and went, and I went to DC and gave a talk at OSDF, it's an open source digital forensics conference. I stood up there for half an hour and said, I've written a Java program to do something really useful in the digital forensics community. People said, fair enough. And I revisited that talk in February this year, when Nimrit said, you know, you're coming around in June. And I thought, oh, this is just dry, it's great for forensics, there's no, to stand up and say, I've written a Java program to do X. My audience is going to say, well, how does that benefit me? You know, so that got canned, this tonight's talk. Then I thought, well, I've got this API, this auto-generated C code project that's never seen the light of day. I'll talk about how my system is as good as the kind of open source reference in dynamic program analysis, which is this system called Cuckoo Sandbox, which you can go to online, and you've got a binary program. You don't have to do any programming with Cuckoo. You've got a binary program, foo.exe. You give it to Cuckoo, it runs it in a virtual machine, Sandbox, gives you the results. And it's doing API hooking. So it says, this program opened a registry. This program is listening on a port. This program wrote a file. Okay, so you get a very good, minuscule view of the program as it executes. And Cuckoo is, kind of, you can pay big money for these things too, but Cuckoo is an open source one, Python and C. And I thought, I'll talk about Cuckoo and my stuff and this Microsoft API hooking enabler called Detours. And then I thought, well, that's for a C audience and a kind of system level Microsoft hackers. There's not a lot of Java in there, but there was some Java in my C automatic kind of magic generation, and that was Antlr. So I've ended up focusing tonight on Antlr, with the cyber stuff maybe hopefully at the end, but hopefully you'll get to take away that Antlr is a great technology for manipulating text, basically. In my case, C source code as an example of that text. So finally, after however many minutes, what is Antlr? To quote from the Antlr website, it's a parser generator. You describe a language, you press go, and Antlr spits out code that when run against programs in that supposed language, can A, tell you that's valid or it isn't, and B, will let you manipulate that program, either by evaluating it or building something useful like a tree that I can then manipulate. Okay? Terence Parr, the author of the book, says he's been doing this since he was a grad student, going back a long time. So it's developed over the years. He's added new features, but at the core of it, it's an amazing parser generator. That's what it is. Okay. So I'll let you read that. It's in this book. I just love that. I thought I had to share that with people. The second of those quotes is kind of haunting me, having looked at how long I've been working on this problem. The 5 years that is relevant to me. So how many times have you seen a computer science book with something you could laugh at? I thought that was fabulous. 2 levels of indirection away from doing anything useful. And you mentioned physics. So the physics guy thought the programmer didn't do any work. So, why program by hand in 5 days what you can spend basically 5 years of your life proving I can automate this, it must be a better way of doing it. Who's ever been there? God, I've certainly been there. Okay. So, continuing on. Why would you want to use it? Does everyone know or everyone heard of a REPL, a read, evaluate, print loop? You normally type some stuff in and out comes some answer, okay, in some language or some varying levels of complexity. So if you're learning how to do that, and there's a great thing to use. If you want to go a bit more heavyweight, hence the exclamation mark, you want to build a new language that can do useful things like Java++, or whatever, C++, if you're building a compiler, that's a big deal. Okay? So Antlr is a very useful tool if you're building new languages. Remember a guy said to me in England, if you can't write a grammar, you're trying to parse some text, and you can't write the grammar for what that text should look like, you will never write that parser. And it's so true. So in Antlr, we can just write our grammar and let Antlr do the heavy lifting. If we're not writing evaluators or compilers, what happens if you've got some pilot XML and the customer says, I need it in JSON? XML is structured enough that you could use a tool, Antlr or similar, parser generator. You could describe XML in a grammar, kind of DTD, and say, Antlr, write me a program so that if I spit at you an XML document, you can write out the equivalent JSON. That's a very useful tool to translate A to B, given A is structured enough and B is also structured enough. What we can't do, what Antlr's never going to translate is English into Finnish, as you can probably appreciate. So, the exclamation marks are a not trivial task, and the question marks are meant to say Antlr's not the tool. How natural language translators work and Google and that sort of stuff is just beyond my comprehension. So the first step, if you've got a text document, Java source code, Python source code, some CSV, it's text, it basically is text processing system. You're saying to a program, make some meaning of this. So the first stage in recognizing a language, a token stream on some input from a string or a file, is what's called a parser. So if anyone didn't know what a parser was, hopefully you do now. And a parser generator does what it implies. It generates that parser code for you, so you don't have to do it yourself. And that's what Antlr is. Okay, another tool for language recognition. Any questions? Okay. So before I forget, or near it says it's 8:45, some things I wanted to get out now, so maybe people get interested at the end. They can say, oh, you mentioned X, Y, and Z. The book's fantastic. The papers I forgot to bring, this amazing paper, this one here, not Antlr specifically, but a system that Par also wrote called StringTemplate. A few months back, I couldn't come to SeaJUG. Someone presented on a templating engine, and at the very time I was reading this paper, and I thought this would be a great paper to bring along to the talk to say to the person, have you ever seen StringTemplate? So there's a fantastic paper to read. He talks about a rigorous way of saying what a templating engine should and shouldn't do. It goes back to the old days of Java server pages and how horrific JSP was, because it had the full power of a programming language. Okay? So at the time there was no real definition of what a templating engine should do or could do. And he talks about all philosophy and an indexing scheme in that paper to say this templating engine, like Velocity or Tapestry or whatever, violates so many principles that it shouldn't even be called a proper templating engine. So that's a great paper. The website is a great place to go for all and resources. The Detours paper I've also forgot to bring. If you Google Hunt Brubaker, they Microsoft employees at the time, not sure if they still are. That'll give you a description of Detours. I've got a nice kind of graphic diagram that hopefully will explain what detouring with API hooking with the system detouring is. The expression toy language and all the code built around it that I'll show tonight, I've bundled up as a Git archive, as a zip that I'm willing to share with people. If you want to leg up and, what was Stuart doing? I'd like to see the code some more. I'll email you the code. And I'm hoping in the next few days to actually get this stuff out the door. I call this Windows C as Java objects. So the kind of C generation code I've built as a Git repo and a Maven system, I'll put up on GitHub. And kind of the motivation behind doing this talk was to actually get this work finished. So I kind of forced myself, you've got to do this stuff because you're going to give it a SeaJUG. So I'll try and get this stuff onto GitHub. So, okay, let's talk about how do I use Antlr. I build a file, t.g, and then I give it to Antlr. And Antlr produces t-lexer, source code Java, and t-parser.java, source code. So this bit's my work, and these generations of code are Antlr's work. And to run it, I just need whatever jar that class is in. And I give it my grammar file on its line argument, and then I list what I've got, and it's produced this. Okay? That's given me a program that can recognize programs written in the language T. I need a test rig to run the parser. And I'll show various test rigs or kind of runners. So if I build a run T program, build the whole thing, run my program with Antlr in the class path, I've got a test rig that can exercise the parser that Antlr built. Does that make sense? Okay. So of course, nobody writes Java, Java C, Java and stuff from the command line. Well, maybe they do, I don't do it anymore. So how Antlr plays nice in Maven and how Maven just takes care of all the stuff, you just say in your POM, I'm going to be using Antlr because I've got Antlr grammars involved in this project. So you just name the Antlr Maven plugin in some version. The group comes from Antlr.org Antlr. And then given you've used the parser, in my case especially, I want to walk these things called trees that Antlr's going to produce. So I need the tree API, and that's in this regular dependency. Does everyone understand Maven POMs? People? Yeah? Okay. So it's a fairly straightforward couple of Maven elements, and now my project is Antlr powered for very little effort on my part. Okay. So, talking about where do I put all this stuff? Well, the standard for Antlr grammars in Maven is source main Antlr 3. I'll come to why it's 3's here in a bit. So I build my grammar file, I put it here. I build my runner, I put it in the regular place. Antlr supports Java packaging, but for now, let's not worry about that. We'll put it in no package. And I say to Maven, build my system up to the compile stage, and Antlr runs against the G file it finds in the file system and produces the Lexa file and the parser file. And then we build the whole lot and we end up with a system that we can run. Okay? If you're interested, Antlr binds to the process sources lifecycle phase. So if I say name process sources, I'll get Antlr to run, but then obviously I won't have anything compiled. But most of the time you just say name and package and the whole thing is done. And if I edit my grammar file, say it again and the whole thing is done again. You never really have to look at these other than the first time you've done this and you're interested to see what does this Java file look like? This is Java source code, I've got to have a look. Okay. So I should mention what the difference between a Lexa and a parser is. Imagine some stream of characters on your input, A plus B times 7 times foo plus 4. Okay. The job of the Lexa is to recognize groups of characters and turn them into what's called tokens. Okay? So the job of the Lexa is, if we define variables, identifiers in our language, the job of the Lexa is to see FOO and then white space, and to say, I'm going to call FOO an identifier token, and I'm going to call it foo. And then the Lexa will give that token of type identifier and, if you like, payload, foo, going to give it up to the parser. So the Lexa reads the character stream, and the parser reads tokens from the Lexa. And in Antlr, they've made these into different classes, which I think is a nice way of distinguishing the different responsibilities of the different parts of the parser. Okay, so your first Antlr grammar. Okay, this is an Antlr, a .g file. So you start off with the name of your grammar, basically the name of my language. This is a toy expression language, expra, or maybe x.g. First line is a keyword, grammar, the name of my grammar, expr. Okay, and in the grammar file we support C style comments. So the first part of my grammar to describe this language is a set of tokens. I'm going to say white space is defined to be a space, a tab, a carriage return on the line feed in these parentheses and then a plus. So that says if you see a sequence of white space, this means one or more, you can call that a white space token, and what I want this parser to do is skip this. So basically, this Lexa, this parser, is told if you see white space, throw it away. Don't build a token with just white space in it and supply it to the parser. Because in this particular language, the parser doesn't care about white space. Okay. Has anyone ever heard the term BNF? Backus-Naur form. It's the syntax for writing grammars. So Antlr relies or is influenced heavily by the Backus-Naur form of parenthesis and star to mean 0 or more and plus to mean 1 or more. Okay? So it's kind of Antlr influenced BNF syntax. Okay? So the second token I'm going to build, I'm going to call int. And I'm going to say an int token is any sequence 1 or more of decimal digits. So from there you can see this language can't support negative numbers. Okay, this language can't support negative numbers. Okay, but tonight, who cares? So 0 or 57 or Googleplex, they're all valid sequences of characters that conform to this rule set that says that is an int. When the Lexa sees 1, 2, 3, 4, 5 white space, it's going to say, I found an int. And at that point, it's still the character stream 1, 2, 3, 4, 5. It is not 12,000 whatever. At that point, the Lexa will give a token that's an int type with that payload to the parser. Okay, so that's numbers. The third part of the Lexa is identifiers. This language I'm designing is going to have identifiers in it. So you can imagine variables. Wow. Okay, so my variables are lowercase, uppercase, A through Z, as many characters as I like. Okay, and they're the only tokens. The only token types I need to build. So white space I'm going to throw away, but I have to tell the Lexa I want to throw it away. Okay? The lexer has to know what to do with every single character that it sees. Okay. So after the lexer part of the grammar is the parser part, the kind of heavyweight bit. The thing that's going to take this stream of tokens coming at it, and it's going to try and organise them in such a way as to say, this is valid, this is a valid program. You know, when you type a big Java file and hit compile, there's a parser in there saying, this is correct Java. Oh, there's a syntax error, you've got a trailing brace missing, or whatever. Okay. So this is a very simplified version of that. So an Antlr grammar says the first rule shall be the entry point for the parser. So this, the way to read this, so I was going to highlight things, just remember. The way to read this is, a program is a sequence of one or more statements. Okay? Well, how do we define what a statement is? A statement is an expression followed by a semicolon, or an assignment. You can hopefully intuitively see A equals 17 would conform to that. An assignment expression followed by a semicolon, or a semicolon by itself. Those are the three alternatives with the vertical bar that make up a valid sequence of tokens that make up a statement. Okay? And what's an expression? Well, an expression is this rule. An expression can be defined as a multiplicative expression, for sure, followed by, look at the outer brackets, 0 or more with the star, 0 or more multiplicative expressions preceded by a plus or a minus. That's what that means. So you can imagine seeing some source code that said A plus B minus C, because we've got as many as we like of trailing sub-expressions. What's a multiplicative expression? It's an atom, which we'll come to, followed by 0 or more tokens that are times or divide followed by another atom. Okay? And the order that we've written these two rules in influences the precedence of the language. You know, the precedence of Java and multiplication is a higher precedence than addition. It's because the way the grammar is written defines how the parser attaches meaning to the program. Okay, so in this toy program is actually enough, these two lines are enough to show you how precedence of programming languages work. Okay, if I substituted the product and the division operands with here, I would have a language where plus and minus are higher precedence than times and divide. Okay? And finally, what is an atom? An atom can be an int, which is this token, or an ID, which is this token, or it can actually be another parenthesized expression. So this language supports parenthesized expressions already. Okay? And that's it. That's a powerful enough system in one page to recognize, you know, a lot of different programs, shall we like. You can probably imagine some that you would type in and see if this thing works. Do that. Okay, any questions? Yeah?
Do any of these words have meaning in Antlr, like the int for integer?
No.
They're all,
no.
you've defined all.
I defined this token type. Yeah, you couldn't put lowercase in there because it's kind of building Java source code. It would complain. When Antlr read this file, if this was lowercase int, I've never done this, but I can imagine it would say, I'm going to be producing Java code, and that's going to clash. So we can't do that. So, how am I answering your question?
Well, I mean, if Antlr doesn't know about an integer, it doesn't know the meaning of an integer?
No,
Except that you've defined it as 0.
True. Antlr doesn't know the meaning of integer, but because Antlr is producing source code, if you're unlucky enough to say lowercase int, Antlr probably will produce it. I've never done it. It may warn you. It may say, I'm producing Java code. You don't want to call that int because it's going to clash at the Java compiler stage. Okay. But the answer really is no. Antlr does not know anything about that as being an int. Only my mind knows what int means at that point. Okay. So, yeah.
Does it have reserved words or reserved characters within your grammar, such as skip? Anything within braces?
Yeah, anything with braces is called an embedded action, thanks, and I'll come to how to do those to make a little calculator program a bit later on. So is there any other keywords in grammar, in Antlr? The grammar word is keyword to Antlr. The colons, I guess, it needs to know where they are. The parentheses, it needs to read. The 1 or more or 0 or more, it needs to read. You know, if you want, how do I distinguish this token in this document from this token? Well, this is in single quotes and this isn't. So you do have to be careful. And I have to say, if you make a mistake here, at least with that version of Antlr that I'm using, it's not particularly easy to see the error when it kind of blows up. Okay? Maybe with Antlr 4, and I'll come to versioning, it's a bit easier. But has anyone seen any kind of grammar that looks, is this totally double Dutch to everyone? Or you can't say, it's a B and F. Okay? If you're ever using a programming language reference, if you're an old C programmer like me, looking Carnegie and Ritchie, at the back, Appendix A, the C grammar, you go, oh my God, horrific. Okay? But in Java books, in Python books, there has to be a grammar. How can you write a compiler or something for a language without a grammar? Okay? So this is a grammar for a very small language on a page. And I think that's pretty cool. 13 lines, actually. Okay, why do I care about the number of lines? I'll show you in a minute. So, go back through my rules. I've got 5 rules and 3 token types. And I'm going to output Java code. And there it is. So given a G file, first thing you do is, I want to see what code it produced. So I find in my generated sources, file system in Maven or wherever, it's generated expr parser. It's just taken my grammar name and tacked on the parser keyword, and it extends from some Antlr thing, and he's put comments in where he saw stuff in the grammar file, and my rule, my prog rule name has become a member function name in the generated Java class, and so on for stack. My stack rule has become a member function, and you can imagine in your mind how this code works. It takes the input, it starts off a prog, and it descends into the input stream, into the program. You call it a somewhat grand name if it's just A plus B, but it's a program, and it's going to call these various methods that are driven by how the grammar was written. Does that make sense? Okay. It's even said, you know, I got this from line 40, column 1 of the grammar file. It said this in the grammar, and I'm going to turn it into whatever the implementation of stack is. Now, I've left the actual guts of these methods out because they're pretty hairy, as you can imagine. Something that is generated to recognize programs in a certain language is not an easy piece of code to write. And it's amazing to me that it works at all on even something as small as a language which has got half a dozen token types. But this thing really works. Any questions? Okay. So, let's look at what produced. I'll just sit back and try and be quiet. For those that aren't Unix people, WC is just a word count program, and -L just tells me how many lines. So hopefully you could have ingested that slide. My effort was 13 lines. Okay, I had to learn the question.
Well, just to be pedantic, how many of those are actually the comments?
Okay, good. I knew someone was going to say that. Someone, yeah. I included my comments in my 13 lines. I did not say that was 1, 2, 3, 4, 5, 6, 7, 8, 9 lines, which I could have. I said, oh, that's 13 lines, because I knew you were going to say that. So, there's plenty of comments. You see 4 on the screen. It's commented, but the sum of those 2 numbers is a lot bigger than that. The moral of this is, it's really doing the heavy lifting. Okay. that satisfy your question?
I'm just smiling because we used to have to write those.
By hand?
Well, as a problem set. By math class. We used to have to write I was about to say you're halfway to a list.
Wow. You would write parsers in class?
Well, there's a problem set.
Ah, cool. I'm very glad you were there. Okay, so the moral of the story is Antlr is doing the heavy lifting. Okay, but not only can it produce Java, one line change in my grammar file directs Antlr to say, I don't want Java, I want Python. I want to do the rest of this problem in Python. Antlr is a Java program, a bunch of Javas, but doesn't necessarily create Java source code. That's pretty cool. If you're not a Java shop, you're a Python shop or a C shop, but you need the power of a parser generator, but you can't afford for it to just spit out Java, you're in luck, because Antlr can do Python. Anyone ever use YAC? Back in the day, yeah? It's spitting out C, and that's what you're getting. Is that right? It's a C?
Yeah.
Yeah. Antlr's kind of come on 30 years after that, and it's ongoing. Antlr can spit out Python, and you don't have to decorate your grammar other than one line. That's really nice. Okay? It's generated, you just crank the handle, and out comes 2 Python files. You do the rest of your programming, the rest of your XML to JSON transformation, you do it in Python. Antlr's built the parser for you. It can do C. Language equals C. Rest of the grammar, rest of the 13 lines, unchanged. So I've added 1 line, so I've got maybe 14 or 15. And what's even more amazing, you can imagine, oh wow, the grammar, the parser generator, the Antlr tool has been told to generate Python. There must be a bunch of Python-specific output in that Antlr tool to generate Python source code. But he's abstracted away the production of the source code from the way that the parser has to work using this thing called StringTemplate, which I haven't particularly used, but I'm just getting into. Another technology from the same guy that wrote Antlr, Terence Parr. The templating engine I was alluding to in one of the earlier slides. The core generation logic that says, given this grammar, how would a parser work, is the same, and it just uses StringTemplate to say, I want to spit out Python, I want to spit out C, I want to spit out Java. And there's also other languages. I know it does JavaScript, C#, I think. If you go to the Antlr website, you'll see if you have to write the rest of your problem in a language other than those 3, it could be. So for C, it generates a header file and a C source. Any questions? Okay. So that was the grammar. I wrote the grammar for the toy expression language. Antlr generated the Lexa file in Java, parser file in Java. How do I build a program, what I call a test grid? So I've written, this is my code, I've written an expression runner program. I've imported Antlr's runtime classes. That's why I made when I needed that as a dependency. So I'll start off, don't know too much about the parse tree builder myself, but the first object to build is a parse tree builder. And I think this token here has to be the first rule in the grammar. Won't stay too long on that. The next line is, as you can imagine, I've got some string like program on the input, and I need to feed that to Antlr. So the first thing to build is what's called the character stream, and this can be a string stream or a file stream or some other Antlr way of getting the text into your program. In this case, I'm just reading from the string, so this string matches this string here. Okay, so now I'm kind of getting somewhere. That'll give me a flurry of characters on the input. And it's the Lexa that wants to see those. So the generated Antlr class, EXPR Lexa, is what I construct, passing in the constructor this char string that I just built. Okay, this is just an interface that when he generated this class, obviously implemented that interface. Going one step further on, well, I want to turn what comes out of the lexer, it's tokens. So the output of the lexer is, here's the token foo, here's the token equals, here's the token 763, here's the token semicolon, here's the token plus. Okay? So the token stream is something that can offer tokens to the parser. So we have to build this token stream, passing in the constructor, essentially the output of the lexer phase. Is this kind of intuitive? Yeah? Okay. So the next thing, and the real meat of all this, is the parser object itself. Antlr generated this class for me. I just build one and pass it 2 arguments, the token stream, and going way back up to the parse tree builder, which I know why he needs it now. And then we say, run the program. And the parser will walk and run on that input stream. Okay, and then when it's done, I want some result. And in what we've got with the grammar that we've written, all we can really do is ask Antlr, ask this parser, print out what you did to read the program that you read. Okay? So, if I run that test rig, if I run that EXPR runner, and I type in the number 1, semicolon, what I get printed out is the parse tree. Essentially, the methods that Antlr called in that generated class that make that a valid program in that language. So it basically descended all the way to say 1 is an int, and that's a valid atom. And a valid atom is a valid multiplicative expression. And if all there is a multiplicative expression, that's a valid expression. And when it recognizes the semicolon after the 1, it says the expression plus the trailing semicolon is a valid statement. And the 1 statement that it's read is a valid program. And now it's got to the top. So if Antlr can descend and call the prog method and come back from that, the program is basically finished. It's read all the input and it's satisfied. That's a valid program in that language. Does that make sense? We haven't seen any results other than, hey Antlr, what did you do to turn, how did you warp those 2 tokens in my input program to confirm that that program is valid or not? Okay? So here's some more things I can do. If you remember, we had identifiers, we had assignment, we had multiplication, we had parenthesized operations, we had the basic arithmetic operations. Okay? So I wrote a little program that I'm offering anyone who wants it to copy. So if I say my expression shell, blah, 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 plus blah, 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 again, it's a valid program. It says, oh, I found these 2 atoms, this atom here, plus this atom there. It doesn't know what any of it means, but it's valid text in the language that you defined. Okay? So I could type at this thing all day with anything that conforms to that language, and it would say, this is how I got there. So we're already onto a useful program. It can take a program, this garbage here, and say, yeah, that's valid against the language that you defined. And what's even better is, it's great when you make a mistake. If you look at the grammar, 1 equals 2 is not valid. Because nowhere did it say that int could equal int. Okay, but Antlr actually staggers on. It doesn't just blow up like Yap used to say, and that's all I'm doing. Antlr will keep going and just localize the error and still go on and do other things. In this example, this is another deliberate mistake. A equals semicolon. That's not valid in the grammar. There needs to be something there. But this bit's valid. And Antlr will show you, oh, I got through B equals 7. So it's very good at error handling. And what I haven't really ever used, and certainly haven't got time to show you, is in the book they explain how you can do elaborate error handling by adding code in the grammar that the generated parser class will pick up. So you can do all sorts of great things with error handling. I just want to point out that it doesn't just die when it sees the first syntax error. what you're probably realizing is, okay, all I've got as a result is a parse tree. How did Antlr walk the input language? That's essentially, other than academically, that's essentially useless. Okay, you probably want, I want a calculator. When I say 4/3 pi r squared and r is 10, I want to know the answer. Okay, what's the volume of the sphere with the radius 10? I can define that in this language, but currently I can't get it to do anything. I can't get it to compute or to evaluate anything. So we've got a valid grammar and a valid language and valid programs or invalid programs, but we haven't really got anything done. Okay? So we need to add one method of getting Antlr to do things is to add actions. Okay? So I've come along with an expanded Antlr file and I've called expression actions.g. Now you'll start to recognize things that are definitely Java flavored. I'm going to need in my program some state. If I say a equals 4 and then print out a, you expect the answer 4 to come out because you intuitively think it's a programming language. If I say a equals 4 and then later on I say a, your mind just looks up the code to see, well, the last assignment to a was 4. So the value I expect printed out is 4. Is that true? Yeah, hopefully. So to remember that a equals 4, I have to have some memory. So it's just a regular Java map. So you can embed, you can tell Antlr, in the generated Java class, I need this code to be added. Okay? And to do that, I need the Java compiler, obviously, to know that when I say map, I mean Java util map, so I can add import statements that Antlr takes verbatim from the grammar and dumps in the generated source file. Okay? So now I have some memory in the program. So now the program is still a set of statements. That hasn't changed. But now we're adding embedded actions. So everything after the BNF style, the BNF part, everything after that says a statement is an expression followed by a semicolon, or it's an assignment, or it's empty. In the first two cases, the syntax says, I want to just system out print line in Java, and then the syntax in Antlr to evaluate, to get hold of the value of this expression is $expr.value. Okay. So that's how to print out the value of that expression. If it's an assignment, we actually want to store that in our memory. Okay. So we ask, what's the name of this token that's an identifier? Is it foo or is it var? If you evaluate the text of the token, you get the string foo, and that's going to be the key in our map. Okay. So imagine this says a equals 4, we're going to be storing a as 4 in our state, in our memory. So to add embedded actions to the expression rule, we need to go a bit further. We need to tell Antlr, we're going to do some basic Java computation here. I need a return value for the method that you produce that's called expr in the generated class. And we're going to assign names to these subrules. What this says is, when you've evaluated this multiplicative expression, I'm going to call it E, and I'm going to take its value, and I'm going to assign it to my return value. Okay? And if I see more things that satisfy this rule, I'm going to assign a name to whatever this is, and I'm going to add that value to my accumulating value. So hopefully you can now see, when it sees a plus in the program stream, we're doing Java addition. And when we see a minus in the input stream, which Antlr doesn't know, and essentially this is not a Java minus, this is a minus in my toy expression language, then it's going to say, well, this means, in fact, this is the association that in your mind you think, well, it's going to do a subtraction here, but I could do anything I like there. It would obviously be a pretty crazy program. But if I swap these two over, if you saw 4 minus 3, you would get the value 7. We know what you expect. Okay, so this is how we accumulate the result of this expression rule in Antlr with these embedded expressions, embedded actions, I'm sorry. Any questions? Okay. So we're going to do two more, and it's the same kind of flavour. If I see the rule called multiplicative expression, I need to say, Antlr, we're going to build a Java int, and what we're going to do is, if we come to the first, the multiplicative expression is just actually one subrule. So it says, when you evaluated the atom, call it E, and call the value I'm accumulating E.value. If after the atom you see some operations that are times something else or divide by something else, we're going to again, if we see if it's A times 4, we're going to do corresponding Java operation. So it's a little toy embedded action that almost one-to-one matches the operands in the language that I'm defining. Does that make sense? And finally, the atom rule, how to add embedded actions for when Antlr goes down and says that something is an atom. If it sees an int, like 45, it's still at that point the text 45 as a token. We're going to call this in Java to convert the text of that token, which is what this produces, into a Java int, and then we're going to store it. No, I'm sorry. If it's an atom, it's just an int. The value returned from the atom method, if you like, is the value of the int. That makes sense to me, at least. If 47 is the token, 47 is the token on the input string, that value shall be 47 as a number. If the token on the input stream is an identifier like foo, we want to know the value. What does foo evaluate to at that point when it was read in the program? We just look it up in our memory. Okay? So we can take the payload, the string value foo, from this, which is id.text, and look that up in our state variable memory. Okay? And how to evaluate something in parentheses. The parentheses, although they're needed as tokens in the input stream, they don't contribute to the answer. So the value of an atom, if it's something in brackets, is just whatever's in the brackets. So you'll see here that the value we're updating is property solely of the expression here, not of these two. Okay, does that make sense? Hopefully. So that's it. That is basically turned the toy expression language that had nothing going on in the parser into a mini calculator. So how do I build that? Well, all I do is I go back to my test rig, and where I did have expression lexer, I've now got expression actions lexer, because I've got actions in the generated program. I've got an actions parser, so I replace a few tokens, and I say go. And it walks the input stream, the program, but now it runs the embedded actions at the places that it sees them as it walks the tree, as it walks the code, and builds up, as it evaluates the rules, I should say. Okay? So my code is really no different. The embedded actions went into the Antlr source file itself, into the grammar. Okay? So to run that, I've got my test rig, extra actions runner, and I can just type at it, and now I'm getting evaluations. If you look back in the grammar, A equals 5 didn't actually produce the output. It just stored the value 5 in the memory for A. And B equals 4 times A, well, it will look up A in the memory and find 5, and it will multiply that by 4 and assign that to B, but again, it won't print anything. Only when I just evaluate an ID by itself do I get a print line in Java. So I've basically got a mini calculator. Okay. So one thing I added to this little runner that you could see if you get the code from me is this little a command in the runner called L to load the program from file and evaluate it. So I don't have to keep typing, I can basically load the program. So if we look at the geometry program, a bit grand to call it that, I jump to my editor, No, I'm not. No, I'm not. I'm going to carry on because on the next slide I've got something that's basically the same. I say run the demo for a clearer picture, but I'm just going to go to the next. There must have been things in this program that evaluated to these numbers, is what I'm trying to say. Any questions? Okay. So, if I built a program called circle.exp, I just dreamed up the .exp file name and some kind of grand notion about, wow, I've written a programming language and exp is my file suffix of choice. If I say pi is 3, probably thinking pi's not 3, pi is 3.14, blah, blah, blah. In the grammar, in the language, we didn't have floats, so I'm stuck for now with pi equals 3. So, oh, sorry, John. So I can define a variable, radius is 4, diameter is 2 times radius. So I'm doing some common operations on circles and stuff derived from circles. So at the end, to see my results, I need to just ask for them to be printed out. So if I run my little runner with the embedded actions in it on that circle, then I get these numbers. So now we essentially have a calculator. Yeah? Isn't that cool? That's way cool. All I did was sprinkle a few actions to do memory updates. I did the plus and the minus and the times and divide, but I didn't write any other parser. Antlr did all that. And it pulled my actions at the appropriate times as it parsed the source code, the input program. Okay. You would find out if you were to do that. You can only go so far with a system that calls actions at the time that it sees those tokens on the input stream. Okay? That embedded actions little calculator where I say a plus 4 and it can just evaluate that straight away because it's got everything it needs right there. If it's got a memory that says a was 5 and it's now looking at a plus 4, it can say 9 straight away. You can well imagine that if you're parsing Java or C or something more complex, that method of writing a system is not going to work. So what is good? A system, a data structure called basically a tree in kind of the domain of parser generators and language processing in general, programming language processing. This is called an abstract syntax tree. Has anyone ever heard the term abstract syntax tree? Yeah? Okay, most people good. So, Antlr can do trees as well, which is just fabulous because I needed something I was going to, and hopefully show, I wanted to take C code and generate more C code, and C is a horrendous language to parse, so I used the power of Antlr producing trees in my problem solving. So if you've got a problem with a complicated enough input language, then trees are the way to go. Because you can't do the calculator for very long. Okay. So I go back and I write a third grammar. I'm done with the plain grammar that had nothing. I'm done with the embedded actions grammar that evaluated things as it walked the input stream. Now I say to Antlr, I want to build abstract syntax trees. So you say in this third grammar, that's called exptree.g, with the name of the language is exp_tree, you say to Antlr, I want trees. Okay? That's a very big change for a very small change in the input. What it will produce is very different. And I'll show you why. And the next thing I need to do is I need to say to Antlr, I need some dummy tokens. What this means is, even though you'll never see this on the input, on the program, I need you sometimes to produce these dummies. And I needed this particularly because I want to take a C program as input, remember everything about it so that I can output a variation of it. Okay? And because you normally discard things like semicolons because they just delimit statements, I can't afford to routinely discard things because I need to maybe generate them back on the output. Hopefully it'll become a bit more obvious what I mean in a sec. So just bear with me that I need to define these dummy token types. Okay? But given that I need to do that, we'll start going with how do I decorate my grammar so that Antlr produces trees. I'm in charge of the shape of the tree. Okay? And that's very important to point that out. Antlr doesn't assert what the tree will look like. In fact, if you don't do any tree decoration, which is what this is, Antlr will just say, this tree is a flat list. And now I'm no better off than if I hadn't read it in at all. Yeah, the program comes at me as a sequence of characters turned into a sequence of tokens. But if it's built into a tree, it's just a flat list, it's really not a tree at all. So you have to tell Antlr the shape of the tree that you want, because in your mind you're thinking of manipulations on that tree. So the first stage in that is to say to Antlr, a program is a sequence of statements. I want you to build a new subtree. This character, the character, says to Antlr, build a new subtree. At the root of that tree, I want this dummy token. The children of that group will be all the statements that you derive from this. Okay? So this, when you see this, it says build a new tree, group it here with these children. Going on to the other rules, this says, when you're trying to parse what does a statement mean, or look like more than mean actually, if you see expression followed by a semicolon, build a new subtree with the statement dummy token at the root and whatever the expression is as the children. I've discarded this token on the input string. It doesn't appear in the tree. But because I've got a problem of, I need to remember that semicolon maybe, I basically have remembered it, because if I know that my tree node is this dummy type stack and I need to output code, I can say, when I visited the children of that, I can just tap the semicolon back as the output. So this dummy token here is essentially a proxy for discarding this token. Okay? And this says, this alternative of this rule says a statement can be an assignment expression. This says, I want you to build a tree shaped such that I'm going to put the stack token as the root, and this tree shall have 3 children. This subtree, and whatever subtree is produced by going into that rule. Okay? And so on for the other two productions, the other 2 rules that I need to do. There is an alternative syntax for anchoring these trees, and that says, when you see this token, build a new subtree from this whole expression anchored at the plus. And that's intuitive, because you think of plus as a binary operation. If you were to think of how to build a tree to represent A plus B, it's more intuitive to think of plus at the top with the operands hanging off. Also, you hear a term called prefix notation for that as well. Some calculators prefix notation. So these are 2 alternative ways of saying to Antlr, I want the tree shape to be thus. You can either do this, what's called a tree rewriting with this token, or you can just say, anchor the tree at this token. Okay? So that's it. Oh no, one more. My atom production says, an atom is either an int, or an ID, or an expression in parentheses. And again, because I'm doing source-to-source translation, I need to remember where I saw these. So although these 2 tokens don't end up in the tree, this dummy token does. So this says to me, when I'm visiting this tree node later, and I need to output this as source code maybe, and this is the root of this tree, I can do open paren, then I can spit whatever this is, and then I can do close paren, and I've basically regenerated these two tokens. Okay? Okay. I'm running out of time. So, how do I build a rig to do tree stuff? Well, if it was called expr tree as the grammar, it's built me Alexa, it's built me a parser, but now it's a bit more involved. We don't just say parser.prog and that's the end of it. We're not evaluating, we've got no embedding actions anymore. All we're saying to Antlr is, you build me a tree from the program that you see. Okay? So through a couple of steps, we finally end up with a tree, which is from Antlr's runtime tree subpackage, up there on the right. Now we can do whatever we want with T. Okay? And where I needed to be at, I needed a tree, can you believe, of C source code, because I wanted to process it. But I didn't have a clue how to parse it or to build the tree. So what I did was, via Antlr got me this far. The rest of the problem was mine to process it how I wanted to. But this, because it was in tree form, was the perfect data structure for me to do powerful things. It is nigh on impossible to take something as complex as a C program, as a linear set of tokens, and to manipulate it. Absolutely impossible. But when it's in a tree form, it's much more amenable to manipulation. And, as I've noticed this in the last week, once you've got a good visualization of the tree, suddenly ways of manipulating it are a lot more obvious than when you're just staring at the text. Okay? So, I've got another runner, my third runner program, this time a tree runner. So now I'm going to type in exactly the same little toy language. I haven't changed the syntax or valid programs of the language at all. When I went from my first grammar to my second, I just added the calculator part. When I went from my second grammar to my third, I've just added tree generation hints to Antlr. The source code and the rules haven't changed at all. The programs still have the same meaning. But now when I read this into my tree runner, it remembers programs. And if I ask to my tree runner, display the second program, I'll do this. It says, because I've got in the back of my mind, is it still valid code? Is it still a valid source? I want to emit it back out as essentially the original. And I can load programs in this language too, and I can list all my programs. So I'll do a few. And I have a nice visualization. I'll go into how I generate that. So if I bail out of this and run my tree shell, my tree runner, somebody give me any valid program in this toy language. Anyone? Anyone? Anyone still awake?
4 multiplied by 3.
4 multiplied by 3, thank you. 4 times 3, semicolon. Pretty intuitive, maybe? Okay, how did I get to that graphic? Tell you in a minute. I should point out, the tree walking shell program is a kind of one-way output to the graphic. There's nothing in this particular example, there's nothing I can do to this graphic that affects this. But when I type stuff in, I can at least visualize it. Okay. Any more? Anyone else?
5 times 5
5 times 5.
plus 10.
What? Just going back to your point, what have you noticed there that you don't have? You've seen what you do have.
Yeah.
What don't you have?
Parentheses.
Anyone? What does he not have, even though he has a tree built from that syntax?
The colon, semicolon.
No, he doesn't have any identifiers, but there's no identifiers in the input. So you can't expect to have identifiers in the tree. The tree can never have, well, I say that, that's false. I was going to say the tree cannot have more nodes in it than the input, but that's blatantly false because I've added these dummy token types called prog and state. What have I not computed? The answer, thank you. When I'm manipulating trees, I'm saying to Antlr, build me a tree with the shape that I say, It doesn't give out 12. We haven't gone that far. At this point, we're not interested in evaluating. We're interested in it being expressed in a two-dimensional data structure, a tree, instead of a horrid one-dimensional data structure, which is a sequence of the input, like this. So what was your program? Say again.
Oh, what was it? It was just
Anything.
5 plus
5 plus 10.
10 equals.
Now 5 plus 10 equals is going to be a problem even in this language because that's invalid.
Oh, okay, times 6.
Okay. Okay. So there we go. There's the inherent precedence in the rules that drive the precedence in the generated tree. We said multiplication is higher precedence than addition. So you can't do that addition until you've got the value of this. You can't, the value of that would be, were we to evaluate this, that would collapse to 60, and that would collapse to 65. But that's, in this case, Nimrin.
What would invalid syntax result in, or
That's a good point, very good point.
series?
Yeah. 4 equals 9, a plus b minus 4. It kind of, 4 equals 9 evaluates to something very bad, but at least it staggers on. A plus b minus 4 becomes a tree built by the parser. It doesn't just die at 9. So that can be very handy. Now in my case, I'm reading C code in its assumed value. I haven't had to address any invalid syntax in my particular case. But it shows it's a good system, robust system for doing that. Yeah?
It's interesting. It's actually looking image magic to. It's using image magic to generate the image, which is interesting. It's
I'll come to that in a sec. It's
Okay.
not as magic as you might think. There might be some Maclean involved in that. Okay. But we can type all day, or we can load circle.exp, because it's the same programs and just building something slightly different. Wow, it's getting useful already. So the syntax probably said pi equals 3, radius equals 4, the diameter is equal to 2 times the radius, the area is equal to blah, blah, blah. And then you see down here how this is the nested at the bottom of the tree. Were you to evaluate this variable volume, you would need to evaluate that first, because this needs 2 operands, and so on. Okay? So the subtrees hanging off the end are just because in the input program pi-rad, I wanted to print them out when I was doing the embedded actions. To just say an identifier on its own isn't particularly interesting when you're representing it as a tree. But isn't that pretty cool? We get a huge benefit of being able to visualize the trees that are built, and better, how we can manipulate them if we can see them in 2 dimensions rather than 1. Okay? So, make sure that I can still... Now, when I read these programs in, I've thrown the syntax, I've thrown the sequence away. I've built a tree, but I've sacrificed the sequential token stream. So if I want to emit a program, I'm asking the tree, I need to walk the tree to visit each node to say, do you need to go in the output? So if I output my program 4, it better would say basically what the input was. Because for now, let's imagine this little program is just doing read a program in, represent it as a tree. Now I want to walk the tree because I want to go back to the program. So if I'm not walking the tree correctly, this output won't be the same as the original. And that could be a problem. But actually in the end, that's exactly what I want to do. I wanted to slightly tweak some C code to make it look like the original, but to have slight differences in it. Okay. So that's what I can do with trees. And Nimrit said it's cool that it used image magic. All that Antlr can do, or one of the many things, all that Antlr can do is a ridiculous thing to say, given what I've shown. One of the things that Antlr can do is build a doc file. Has anyone ever used a doc program? Right, okay, great. There's a package called GraphViz installed, apt-get install GraphViz, and if you install that package for Linux, and it's probably for Windows somewhere on Mac, in there is a program called doc. And doc can read a doc file, which is a text description of essentially a graph. And any tree is a valid graph. So Antlr produces trees. Antlr produces from the trees, Antlr produces a doc file, which is a text file that says these are the nodes and these are the edges between nodes. And then I can give that to the program doc, telling it what output I want, and doc can produce a ping file. And then I can use any viewer, Nimrit, displays the image magic program to render this on the screen. So I just, in my little runner program, I have had Antlr do the doc file generation, because in the first line, the first line says, one of the Antlr runtime classes is doc tree generator. So I build a new one. And then I say, this is my tree. And I say, to doc, please. And Antlr produces a string template. Think of that just as a string with nodes and edges that correspond to the doc output of that tree, regular Java code to print that out to a file. And now, so the output of this Java program is this file, which is the input to the doc program. So I'm going in my Java stroke, my Antlr tree generated program, I got trees, this code gets me to doc, this line gets me to ping, and this line gets it on the screen. Okay? I could use some other viewer. The reason that you saw, hey, that's image magic, is because this is what I've embedded in my toy shell to generate the image on the screen. That's why I say it's a very one-way thing. You know, I'm producing a doc file, running these two commands from my Java program, the image is rendered. It's very much a one-way visualization aim. But it's great, because without that, this whole work is very, very difficult. Okay. Antlr has, as you can imagine, a tree data structure. It's an interface, and it's got all sorts of enticing operations on the tree. It's produced a tree in the shape that I said from the grammar. It's produced a tree from the input program. But now, given this API, I can do all sorts of stuff with the tree. I can add a child anywhere I want. Imagine adding a 5 somewhere, and then emitting the program out, because the program that I emit is delivered by the contents of the tree. I can add identifiers into my input program. I load into a tree, I manipulate the tree, and I spit it back out. You see where I'm going with that? So I can delete stuff. I can ask any tree node, what have you got? I can get at each subtree with an index. I can locate things that have a certain token type. I can get the type of the token type, the text associated with the node. I can do all sorts of fun things, all using Antlr's API for tree manipulation. I haven't had to do any of this. This comes in the Antlr runtime. Terence has provided me the way to manipulate the tree in all these fun ways. So now we're really into recursion. Anyone ever done any recursive programming? Yeah? Trees are just the way to manipulate trees is to use recursion. Manipulating a tree data structure without using recursion is nigh impossible. Okay? Or very ugly at least. Okay, so an accompanying class to the tree class in Antlr is this thing called token. When you were visualizing those trees each of those nodes, and I didn't say, I was highlighting things that were from the input stream in green, basically things that mostly hung off the leaves of the tree, but also binary operands like the plus would be from the input program, it wouldn't be a leaf, because it would have the two operands as its leaves. So the other class that I need to manipulate is this token type, which says the text type it's got, but it also supplies me a way to change the text. So now I can change the identifier A into the identifier B. And if I'm debugging and something's gone wrong, I can also say to the token, your name is ABC and you're an identifier. Where were you in the input stream? Where were you in the original program? Oh, I was token number 57. Well, what line were you on in the file? I was on line 4. That's handy debug context. Okay. So I added to my expression tree runner not only ability to load stuff in and visualize it, but also some operations to mutate the tree. Okay, and I'll show you those working. So if I go back to my runner, I'm going to load a couple of programs, expressions in. Is this going to do this? Yeah. So I'm going to load the circle in. I'm going to load the geometry program in. And then I'm going to list them out. And then I'm going to do this invented operation by me. Replace anything that's an int and has the value 3, overwrite the 3, and write 12. Say. So that's mutated the tree, as you'll see. I've got another mutation operation that says if you find any IDs, any identifiers called height, they're not height anymore, they're the identifier SeaJUG. Okay? So that's a rename. And even more drastic, if you find a parenthesis token in the tree, completely discard its subtree and just write the number 5. Okay? And I'll show you these. And then my final one was just swap 2 arbitrary nodes. Okay? And then emit back out what this program now looks like after all these operations. What I didn't point out was these operations are assumed in this little shell. These operations work on the most recently loaded program. Okay, so I'll show that hopefully in anger if I can remember what they were. So I'm going to load geometry. So there's the geometry program as a 2-dimensional tree. Okay? There's some parenthesized things. In the input, there would have been parentheses around 2 times width. And there would have been parentheses around 2 times height. Okay? I've got a feel for what that may have looked like with the input stream. In fact, I can emit it by saying E5. So it prints back out what you see in 1 dimension as text is derived from the state of that tree at that point in time. So now I'm going to do some stuff like replace integer 3 with 12. So now we've got, was there any 3s?
No.
Was there any 3s?
No.
Oh, there wasn't any 3s. Okay. There's a 2, width equals 2. So let's say replace 2 with 27. Wow, the tree has changed. Everywhere there was a 2, there's a 27. I've done it in all places. I've walked the tree, found nodes that are found nodes that are ints with value 27, thrown that node away, and attached a new child to the parent with the number 2 as a token. Okay? So I can say replace all IDs that were height with SeaJUG. In fact, I'm going to call it this. Maybe you may think I'm lying if I say SeaJUG. So there you go. It's found height, and it said, no, you're not called height anymore. You're called C blah blah blah. Okay. Another tree manipulation operation. And now I'm going to obliterate anything that's a parenthesis. I'm going to replace it with 1,000. So all those things that were like, oh, but I thought I was plus parenthesis width times 2. No. The whole subtree is gone. The parens and everything under it is being wiped out to be replaced by some arbitrary other token that I've defined. And now, you can't even see this on the screen, I'm going to swap two arbitrary nodes. I'm going to walk the tree to find the leftmost node. You can see it, width. You can't see the rightmost node because it's off the screen. But I've got an operation to swap left and right. So over on the rightmost node of that tree must have been the token area of a triangle. I've just swapped two nodes. Okay? Now I can emit the program, E5. And now it's completely different. Okay? You could not have gone from that input to that output, in my opinion, if you hadn't used the tree. Okay? Isn't that pretty cool? You see where I'm going with this? He's going to read this, but he's going to slightly mutate a few things to make it this. Very handy. Exactly what I need. You couldn't have done it without Antlr's tree API and Antlr reading the C code I'll show you. Okay. So there, went through that slide. Replace an integer, replace an identifier, obliterate parens, swap left and right, print it out. Okay? Quick word about everything. Quick word about versioning. Tonight I've talked about Antlr, which is called version 3, which this book adheres to. This book was current when Antlr version 3 was out. Okay? There are other features of this book that I haven't had time to go over. Something really cool called tree grammars, where you basically describe a tree, and Antlr walks a tree. What I've been describing is, here's a token stream, Antlr, you walk that. You can also say, here's a tree, which is the output of the intermediary stage I have talked about, and Antlr could do something with that tree. In fact, my manual tree manipulation is something that Antlr may do automatically, but I don't really understand tree grammars too well. Antlr 4 is current, and Antlr 4 has got a few differences that I don't quite understand, which is why I've got question marks there. I haven't used Antlr 4, but he seems to have deprecated this tree, abstract syntax tree, in favour of parse trees, which I'm not really sure of. I just wanted to get the point across. If you go and say, Antlr's way cool, I'm going to buy the book and dive in, you may not see all the same syntax as you've seen tonight. The reason I'm still using Antlr version 3 is, when I grabbed an Antlr C grammar, which is what I wanted because I wanted to manipulate C code, at the time that I found the Antlr C.G, Antlr 3 was current. So I haven't gone with the Antlr 4 transition because the syntax for how to write the grammar has changed, and I don't want to port a big grammar like C from a version 3 Antlr file to a version 4. But if you're new to this, you definitely go with the latest version. Okay, I'm running out of time. Java essentially finished. C time. I have a little story about this. What we've seen, hopefully, well, you have seen it, maybe you've understood, I can get Antlr to read a program in and produce a tree. And then, given the tree API, I can do crazy things like mutating arbitrary nodes while still conforming to the language. When I replaced SeaJUG or width with SeaJUG, I was careful to say, I'm inventing a new token, still an identifier, just that the text is different. Okay? But if you can do it for one language, like toy language, can't it be done for other languages? Can't I read in C using Antlr to build me a tree, and then I'm going to build the tree? Okay. So here's my little story. And hopefully you'll get to the moral after this slide. So, Mr. Maclean, I see you're applying for the job of senior C programmer in our Linux division. Yes. It says on your resume, 50 years experience in C. Wow. You must have known Carnegie and Richard. Oh, maybe. So, Mr. Maclean, have you ever used signals in your 50 years of C experience? Signals? Yeah, rarely, once or twice. Oh, you have. You'll be familiar with the signal system call. Yeah. Can you go over to the whiteboard, Mr. Maclean, and write down the signature of the C function signal? Over to the whiteboard. Signal. Wow. It's called signal. Yes, Mr. Maclean, I told you it was called signal. It's a function, so it has parentheses. Yes, Mr. Maclean, I told you it was a function called signal. I haven't done any work at this point. Well, signal. My 50 years of experience say signal is a function, 2 arguments, so I need 1 comma. The first argument to the signal call in C on Unix is the signal that I want to catch. So the first argument is an int, and it's the signal I want to catch. Very good. What's the second argument? Second argument to signal. It's the signal handler that I want to install so that when this signal happens, when I get successful, I can jump to my handler. How does that look in C? Oh, it's a pointer to function. That's right, I'll call it H. The parameter to signal, the second parameter, is a pointer to a function that I want called when the signal happens. And that function takes an int parameter, which will actually deliver the signal that happened. And the return type of the function I'm going to install as my signal handler is void, because it doesn't return anything. Yes, Mr. Maclean, not bad at all. What's the return type, Mr. Maclean? You've left off the return. What does the signal function return? Oh, it returns the currently installed handler, if there is one. So, to complete the syntax, it returns another pointer to a function that takes an int and returns a void. And I'm done. That's the end of it. Do I get the job? Oh, Mr. Maclean, not bad at all. What about this abstract syntax tree that you get for that? Anyone see the moral? Anyone? That is a lot more complicated than A plus B. Okay? The moral is C is a nightmare to parse. You know? I mean, this is the ultimate. To me, the signal. Every time I try and write a signal, I have to start from scratch and look it up on the web. How do you write the signature for the C program, for the C function, signal? But you can do it. If I can build a tree that looks like that, I can walk it and spit out something that looks similar but not identical. Okay, I'm in a rush. So my crazy idea was, I'm going to use Antlr to ingest a ton of C header files from Windows into Antlr trees, and I'm going to walk them just the same way as I walked my toy language to produce new code for the purposes of program analysis and cybersecurity, which I was meant to talk about. Okay, I'm going to produce C code, build it on Windows, offer it to an API hooking system like Detours, attach it to a program, and watch that program running. Okay, the generation of the C code will be just as applicable to other operating systems. I don't know if there's a Detours equivalent for Linux. If anyone does, come and see me after. So, running out of time. Windows program execution. Now I'm very quick. You've got some program, binary program, and in it you've written in the source code, create a file. So you run your program on Windows. My program code's up here compiled. The Windows operating system is these boxes. In the Windows system, there's a kernel, there's a DLL, dynamic link library, called kernel 32. Anyone know that file existed? That's a standard Windows system file. In that compiled blob of code, there's a whole set of functions in the Windows API. So the way that you program on Windows in any system is the application programming interface, the API, is just a list of functions and their ways of passing arguments to them. So this function calls create file, this program calls create file, and then this program calls delete registry key. And this DLL has got 900 functions in it. And this DLL has got 700 functions in it. And the socket DLL has got 100 functions. So the scope and the size of the Windows API is mapped. Okay? And any given program could call any given combination of those functions. So, in API hooking, let's go back to where I was. Normally, when I create a file and I give it some arguments, what happens? The program jumps to the create file function in the Windows subsystem, does whatever create file does, and spits me back the result. It's just the way functions work in any language. You pass something in, something happens, you get some result back. Okay? What I'm really interested in, imagine that you don't know what this program is, and you want to see what crosses that line. Yeah? If you can see what crosses that line, you can know what those arguments are. If you can see what crosses that line on the way back, you can know the result of that create file operation. Okay? That's what API hooking is. If you don't know what this program does and it calls some arbitrary Windows function with some arbitrary set of parameters and gets an arbitrary result back, normally you just go call, do, return, the program plows on using X. Okay? If you hook the API, like I say, we're interested in the data that goes across that line. You can do clever things like, when you reach this function, you jump to some other function that you've actually attached to this program. Okay? I put it in red because it's a jump, it is not a call. A jump is a one-way thing. It doesn't come back to anywhere because a jump instruction is just jump. And this is down at the x86. This is the hardware or the machine code for the processor. It thinks it's doing a call return, but the API hooking system has mutated this code, not this code. In API hooking, you don't have to manipulate the call site, you manipulate the called site. And you replace the first few instructions with an unconditional jump to something that you've supplied as a hook. And now, what you can do is, you can log, because this is a jump, you can see, in this function, you can see exactly what these values are. Because this jump instruction could have done nothing to the stack to change those values. So you're staring at A, B, C as your parameters, so you can log them. Okay? And then you call back into the real function. So this is a call return. If the program thought it was really calling WinFun, I need to really call WinFun and get a result back. So I'll do a call, and if you notice, I tried to say that the arrow skips over the jump. So the real program calls something that happened to be jumped. I'm calling the real remainder of the function. Okay? That's a call return. So I get the result back. So I can log it to my logging subsystem. This could go to a file, could do anything. I have basically just discovered that this call passed in ABC and produced X, and I logged it, and the program has no idea. Okay? And then finally, here's the craziness. When I return from this, I actually end up back there. And the program execution continues. Because what we have here is, this is a call, this is a jump, this is a call return, and this is a return. So the instruction pointer ends up back at the call program. That's what API hooking is. It's the hook, the installation of the hook that lets you interrogate the data that goes across that line. Isn't that way cool? I think that's way cool. Instrumenting a program without having any source code at all. Okay, you going to take a picture of that? It's so cool, someone's taking a picture of it. I was quite pleased with that, because I read the Detours paper. It can take a while to understand what's going on. So to have it in a graphic is kind of handy. Okay, I'm running out of time. So, let's imagine that that last call was create file with an ASCII parameter. This is from the Windows API. When you call create file with an ASCII string, you shall pass in these 7 parameters. You shall get back some type that Microsoft call handle, which actually avoids stuff. I want to hook every call that my malware.exe, every time malware.exe calls that function, I want to know all those arguments and I want to know the result. Okay? This is valid C source code, although it's highly decorated with Microsoft's own types, arrived at with something in C called type builds. If you wanted to write a hook to install here and ask a hooking engine like Detours to deliver you that red line, to deliver you that hook, so I'm in charge of writing the hooks, and I'll use Detours to subvert this site to give me the jump, then all I have to do, I have to write the hook and the logging infrastructure tagged onto it. And they will be injected into this process at runtime to become part of the running program. So if I want to hook this, I have to write this C source code. I have to define a variable of exactly this, a variable that's a pointer to a C function of exactly the same signature as the original. So it has to match the return type, it has to match exactly in all the arguments. If it doesn't, it will build, and at runtime it will bomb. Okay. Then I have to write the hook function itself. So I have to write, given some file foo, I can tack on some hook identifier. I need a copy of the text for all the arguments. I need the call convention. I need the return type, all as tokens, text tokens in C. I have to build some logging call that can say, I know we're in create file, and here's all the arguments I'm logging. Then I have to call the real thing, and this, I'm calling a variable that I defined up there, and when I call the Detours attach function, this variable gets magically changed. It starts off pointing at the real function, and it ends up pointing at something called a trampoline that lets me call it to give me that green line in that last graphic. Okay. So again, I have to produce C code to do this. And then when it's called, it's going to return to me, and I can log what this result was. And then I have to write this source code to return the result to the caller. So I have to write that C code to hook that one function. And I have to do that for every bloody function in the Windows API. That is a monster load of C code to write. You couldn't do that by hand. Not for 2,000 calls a week, actually you probably could. It'd take a long time. Okay? The thing is, given this, we're trying to produce something that looks a lot like it. That's the nature of how hooks work. Your code has to look just like the original thing you're trying to hook. If it doesn't, it bombs. If it does look right, you get fantastic monitoring ability of a program at runtime. So that's the C code I need to write. So what I did was, I found Antlr's C grammar about 5 years ago. I think it was just vanilla. It didn't have any embedded actions or any tree construction. I added all the tree construction I needed to say to Antlr, when you see a C snippet, build me a tree of this shape. And then I just said, give me a bunch of header files from Windows. They're all C, valid C files with just function declarations, which is exactly what I need. And load them all in. I get a monster tree of C code. And then I'm going to walk that tree using the same API as I showed you for manipulating our little toy language. Okay? And I probably won't have time to go into this today, but I've managed to solve the problem of what would the signature of the log function be, given that the function you're trying to record is an arbitrary type. So I do want to show this. So how do you get the C API? Well, if you're a C programmer, what do? If you're writing a C program out in front, and you want to use some Windows or Unix system call, where do you go to find out what the parameters of that function should be? Where do you look?
Without H
Thank you. You look in the .h file. The .h file in the C land is the public API of the public part of the application programming interface. You get given the C file and a DLL, or a .a file, or .so. That's the bit that's already been built by the library builder. You're given in Java there isn't that. Java doc is what there is. In C, it's an actual physical part of the language, not just a comment, essentially. So, if I go onto Windows and I write a one-line program in C, Windows is obviously DOS is the old type rather than cat. I'm going to write a one-line C program on Windows. I'm going to ask the Visual Studio C compiler to pre-process it only, not compile it. And that include of one header file is going to cascade into hundreds of nested includes. And I'm going to get a job lot of C functions in the Windows API. That's exactly what I want to take over to Antlr. So I built this shell for my Windows C as Java objects system, just like for the little tree walker in the expression language. I'm going to give it some monster file of C code, and I'm going to do various tree manipulations, and then when I've done those, I'm going to say, now spit yourself back out to C code. Okay, definitely going to run out of time, but I just want to show a few things. So I show this in Angular. Remember, think back to the horrible interview question of the signature. That's a ton of C and looks pretty nasty on one line. Imagine what the syntax tree looks for that. So let me go over and abandon my toy language. You get a lot of trees. Let me go over to something that understands C. I'm going to say, okay, load me signal.c. That's why C is more complicated than my toy language. My goodness. So these are all dummy nodes that I've added to make walking this tree amenable. Things in green are from the source code. Let's see what the source code said. If I haven't lost mine. What did the program? Let's list the function. Emit function 1. So that's the syntax on as a string, but as a tree, it's this. But I can walk the tree. I can say, I need the variable that's a pointer to that function. Give me the return, I can't remember what it was. I'm going to say, give me the return value for 1. And it's going to say, I've walked this tree, these are the tokens you need for a return variable, and it's producing it, it's going all the way to the screen. And this is the syntax you would need. So I've walked the tree and just extracted the bits I need, and if I do this enough times, I can compose the code automatically to write the hook. And if I can do it for signal, I can do it for 1,000 to 3,000 more functions. Should I stop there? Probably should. Okay, I'm going to jump to my conclusion. So C is a lot more complicated than my toy language, but still amenable to tree walking with Antlr. Type defs are the bane of my life. I won't go into them. I did solve that problem. I'll jump to my conclusion. I'll revisit what Parr said, I don't know, in jest, but he said it in front of his book, the whole 5-year, 5-day thing. I've been hacking at this for about 5 years. I thought, God, I could have done this by hand in 3 years. If you, anyone ever tells you, we're doing a project parsing C, just stay out of that project. Although I've nailed it, I think now, I've learned a hell of a lot, but parsing C, especially Windows C with all the decorations that Microsoft do in their header files, it's tricky. the take home for tonight is Antlr is an amazing tool and great fun to use. Tree walking is great. You'll learn recursion. You can do some cool visualizations. Hopefully you'll go away thinking that's something I could use. Okay, I'm done. Thank you.
I would
Any
suggest,
questions?
I was going to suggest if people have questions, maybe stick around.
Stick around.
It's
Yeah.
almost 9, so I don't want to have everybody stick around. But thanks, Stuart.